Okay, back again to continue our lesson. We were talking about the exponential growth. Okay, let's see. We stopped at the example 3. Okay, example 3, population. In the year 2007, the population of a state was 9.36 million people. In the year 2000, it was 8.18 million. So when we see the difference between the years, in the year 2000 it was 8.18, and in the year 2007 the population became 9.36. So we are talking about increasing here. That means that we are going to use the exponential growth function, not decay, because the number here is increasing. Okay, so the number increased between the year 2000 and 2007. The number of people or the population increased between these years. So we are talking about growing or increasing. So in the first question, determine the value of k, the state's relative rate of growth. Okay, we are going at first to put the general function y equal a times e to the power kt. We will take the year 2000 as a reference because it's the initial amount, or we will take the initial amount at the year 2000. So it was 8.18 at the year 2000, and as a final amount in the year 2007 the population was at 9.36 time. The difference between the year 2000 and 2007 is 7 years, and then we can find now k. Okay, dividing, I used the pen here. Divide by, we can divide both sides over to 8.18, sorry, and here over 8.18. Then to eliminate the natural base, we can take the natural logarithm for both sides. After that, 7k will be equal to ln 9.36 over 8.18. The final answer will be 0.01925. And don't forget, again and again, don't forget to write the final equation. So after that, I'm going to write y equal a, which is here 8.18, times e to the power k, which is 0.01925. t, don't put anything in instead of t, because you will use it in the other questions, because maybe they will change it. Just instead you can substitute the values of a and k. Okay, for the next question, when will the state's population reach 12 millions? So I'm going to use the final equation I wrote at the first question. So a, it's 8.18, e to the power, that k, this k we calculated from the first question. T, we have to calculate t because they asked us about when will the state's population. So this is the final amount. Okay, so when the population will reach this amount. Okay, so after dividing by 8.18 for both sides, then here the same things, the same steps. So then taking the natural logarithm for both sides to eliminate the natural base. After that, t will be equal 19.907, which is almost 20 years, almost 20 years. So 20 years from the starting point, which is here the year 2000. We took the year 2000 here as a reference, so it will be the starting point for us. So 20 years after the year 2000, the population will be 12 million. So if they ask you about the year or the expected year, so it will be 20 here, almost 20, plus 2000, which is equal to 2020, which is this year. Okay, anyway, after that, another state's population in 2000. So they give us a population for another state. Okay, was 9.9 million and can be modeled, and they gave us the equation for that city or that state. Okay, determine when the first state's population will surpass. Surpass mean exceed or يتخطى or يكون أكبر, greater than. Okay, than the others. That was 9.9 million. So I'm going to use the two equations. The first one, it's from the equation I found in the first question, and the second one, it's from here the question gave it to me. So when the first one, the first state that we calculated will be surpass or will surpass the second one, which is here. So this equation from the first question will be greater than the last one, or the one that the question gave it to me. So after that, I'm going to divide each side, or without dividing. Okay, we can here to eliminate the natural base, we can take ln or natural logarithm for each side, for both sides. Okay, so ln from the property of the product for logarithms, we can see here the answer after this from the property of product to property of logarithms. We can see that here ln, we can write this term in the form of ln 8.18 plus, because it's multiplication here, plus ln e to the power 0.019 t. Okay, and this is the same here, the same case from the product property of logarithm. We can write this term in the form of ln 9.9 plus ln e to the power 0.0028 t. Okay, after that we can find this at the calculator and this also as at the calculator. Now just we have here to eliminate the natural base, and here also to eliminate the natural base. So after that, it's, I think, just equation. Okay, after that we can use the calculator to find the final answer. So when t is greater than 11.6, that means what the question asked us? That means the previous equation will surpass that equation for this city. Okay, so anyway, this is a guided practice. You can practice at home, and don't forget, you can ask me anonymous about any question you didn't understand or you can't solve. But I think the same question as the question we solved before. Okay, logistic growth. Here they say they refer to the equation representing the state population in example 3 according to the graph. They graph the equation at the right. The state's population will be about 1 billion by the year 2130. Does this seem logical, or I think this unreasonable? Okay, because I think it's impossible that the population will reach that number by this year, because I think they didn't mention the death or the disease in the example. It's just they did. I think they just were thinking about mathematics and how to do everything with numbers, and that's it. But it's not related with our real life. Okay, so populations cannot grow infinitely large. They are limitations, as I said, like disease, such as food supplies, war, living space, disease, death, available resources, and so on. Exponential growth is unrestricted. Okay, so the exponential growth doesn't think about the real life. Okay, it's not always correct, meaning it will increase without bound. Okay, without restrictions. So a logistic growth model, so they create the logistic growth model. Okay, however, represents a growth that has a limiting factor. Okay, logistic models are the most accurate models for representing population growth. Okay, that's the equation for logistic growth, which is the function f of t equal c over 1 plus a, which is the initial amount, e to the power minus bt. It's the same as the previous functions, but just we have a condition here that b is less than 1. Okay, anyway, let's see an application on logistic growth model. Okay, a real world example for logistic growth. The population of Phoenix, Arizona in millions can be modeled. They give us the equation or the function f of t equal blah blah 2.066. Okay, where t is the number of the years. They told you also that the t is the symbol we are using for the number of years. Okay, after 1980. The first question asks you to graph the function for the values of t which are greater than 0, okay, and less than 500. So when you are going to make a table, just substitute by values for t less than 500 and greater than 0. After you got this graph, okay, then I think this is our answer for the first question. They asked us to find the graph or the graph the function. The second question, what is the horizontal asymptote? We talked about the asymptote. The horizontal asymptote is at 2.066. We said that the line will not touch 2.066. It's impossible. Okay, it's approaching, but it's not touching. Anyway, or there is no intersection point between this line and the line 2.0666. Okay, will the population of Phoenix increase infinitely? We are going to say definitely it's not. Okay, if not, the population, what will be their maximum population? Then we will say that the maximum value will be 2.066 million people, because it's approaching to, the line is approaching to that value, but the line will not cross that value. Okay, according to the function, when will the population of Phoenix reach 1.8 million people? We can use here the graph. Here we can see that 1.8 million will be after 50 years, almost 50 years, yes, 50 years. So when t is almost equal to 50, and that's it. We can add 50 to the year to I think, as we did before, and that's it. Our lesson today. This is a guided practice. You can practice at home. As we said, it's the same, I think, and that's our final answer. That's it. Okay, these the answers for question C, D, and B. Okay, so as I said, you have to practice at home. The lesson is very easy, I know, but you don't know when apply something. It's different from just reading and solving by your eyes or by looking at me solving the questions. It's easy for you now, but I think when you do it by your hand, it's different. Okay, so try this at home, and if you have any question, I am ready to answer any question you have. Okay, and thank you today.